Hi everybody, my name is Stefan Lipp. I'm a PhD researcher at the Technical University of Munich, and I'm going to present the tool paper FuzzTastic, a fine-grained fuzzer-agnostic coverage analyzer. This is joint work with Daniel Eisner, Thomas Hutzelmann, Sebastian Banescu, and Professor Alexander Bretschner, which are all with TUM, as well as Dr. Marcel Böhme, who leads the software security research group at the Max Planck Institute for Security and Privacy. So what is fuzzing all about? Fuzzing is a testing technique in which a target program is executed with a large number of test inputs in order to detect security-critical software bugs. The fuzz inputs are thereby automatically generated by a so-called fuzzer, which on a very abstract level has two parameters: the time limit, which specifies the test duration, and the initial seeds from which the test inputs are derived. If a crash of the target program is encountered, this is generally a good indicator that a vulnerability is included and might be exploited in the form of malicious code execution, data leakage, or a denial of service attack. There are a lot of different fuzzers available. All of them implement different techniques, and obviously researchers and practitioners are interested in figuring out which tools perform better than the other. A common metric to perform this evaluation is code coverage. The intuition here is that a fuzzer that covers more code is more likely to detect different or new vulnerabilities and is therefore considered more effective than a fuzzer that covers less code. However, tracking code coverage of a fuzzer or the inputs generated by fuzzer is pretty difficult because a lot of test inputs are generated. And therefore, existing evaluations capture the test inputs stored in the fuzzer queue, which holds the inputs that increased coverage in previous iterations so that they can be mutated for further iterations. Then in a second step, they replay these inputs on a second instance of the same program that is compiled with coverage support and able to actually measure the amount of covered code. However, this approach has two limitations. So first, due to path collisions in fuzzers that hash coverage information, coverage increasing inputs can be overlooked. So they are not stored in the fuzzer queue and are therefore also not considered in the evaluation. So more specifically, for example, we have two program execution paths where one path leads to a higher coverage. However, the fuzzer assigns the same hash values to both of these paths. So even though this path was actually executed, the fuzzer says, okay, it's not interesting. The fuzzer does not add this input, the corresponding input to the queue, and therefore the evaluation also does not consider that input. And in the worst case, this can actually lead to distorted fuzzer evaluations, as we will see later in the case study performed in that paper. As a second limitation, it inhibits measuring how often a code region has been executed. And this is quite an interesting thing because we can evaluate fuzzers from a different perspective. So this would allow us to identify barely tested source code as opposed to source code that has been executed by a lot of different test inputs. To address these limitations, we developed the FuzzTastic coverage analyzer. So FuzzTastic is based on LLVMs, so it works basically with any black box, gray box, or white box fuzzer. And also, other than existing techniques which output the coverage information at the end of a campaign, FuzzTastic allows to report the coverage at a user-defined interval. At default, it's 15 minutes. So FuzzTastic tracks basic block and function coverage, as well as the execution frequencies, which I refer to as hit counts from now on. And not only of the inputs stored in the queue, but of all generated fuzz inputs. In doing so, this addresses the limitations that I mentioned in the previous slides. So using FuzzTastic allows to perform fuzzer evaluations that are not distorted by path collisions. The hit counts enable frequency-based coverage analysis, so we can better distinguish between barely tested and thoroughly tested source code. And the timestamped approach allows to visualize fuzzing progress over time and code. To set up FuzzTastic, the following steps and software artifacts are involved. Starting with the source code of the program we want to fuzz, we first transfer it to LLVM's intermediate representation, and on that representation we can perform analysis passes. So what we do here is we extract basic block data. An example of this basic block data for the program GIF to PNG can be seen in this JSON snippet. For each basic block, we assign a unique ID. We also store the file and the function which the basic block is located, as well as the line numbers that were covered by the basic block. For the instrumentation part, we also use this intermediate representation to perform FuzzTastic's custom instrumentation. The instrumentation is fairly simple. So for each basic block, we instrument or we add a function call to the function that can be seen in that listing here, which just increments a counter in an array using the basic block ID that is passed to that function. So later, whenever this basic block is executed, the corresponding counter is incremented. In the case of gray box and white box fuzzers, we also apply the instrumentation that they need. And finally, we have a binary that we can then fuzz. To monitor a target program and also a fuzzer, there are two parameters that FuzzTastic needs. First, the basic block data that I just mentioned, and second, a fuzzing configuration in the form of a bash script. This bash script contains the fuzz entry and the harness in the case of a library, also the command line interface options, as well as the environment variables, the working directory, the initial seeds, and also the timeout. Once this has been passed to the FuzzTastic tool, the first step is to set up a shared memory segment where the coverage information is stored. In a second step, FuzzTastic then starts the fuzzer. Again, we can monitor black box, gray box, and white box fuzzers, and then the fuzzer just is doing its job. It generates inputs, throws them at the binary, the instrumented binary. So whenever the input is executed and whenever a basic block in particular is executed, the corresponding hit count of the array which is stored in the shared memory is now incremented, and FuzzTastic can query that information in a user-defined interval and write the corresponding coverage reports. An example of such a coverage report is shown in this code snippet here. Again, it's persisted in the JSON format and it stores two timestamps. The first timestamp indicates the time when the campaign was launched, and the second timestamp indicates the time when the coverage report has been written. In this example here, we are fuzzing GIF to PNG with the AFL fuzzer for 2 hours, and the corresponding block coverage is also shown down there in the listing. This is a list where the indices correspond to the respective basic block IDs. So the index 0, for example, corresponds to basic block with the ID 0. In this example here, the very first basic block, for example, has been executed almost 80 million times, which is quite a lot. To demonstrate FuzzTastic's applicability, we generated a large-scale benchmark dataset which can be used for further studies. So we selected in total 12 different benchmark programs which are listed in the table on the left of that slide. And we also selected 9 different fuzzers. So here, for example, we selected the very popular AFL fuzzer and 6 variants thereof. So these are extensions of the AFL fuzzers that implement new techniques that have been that turned out to be very effective. We also included HonkFuzz and also the concolic execution engine Eclipser. Each program and fuzzer pair we launched with 2 different initial seeds. So we used the empty seed and also a non-empty seed corpus. For the empty seed, it's sometimes not possible to really use an empty seed. For example, for JSON CPP, the lowest amount of data required by the input parser are a opening and closing curly brackets. And for the non-empty corpus, we just selected the seeds that are provided by AFL's GitHub repository. We also follow the best practices fuzzing research, so we run these campaigns for at least 24 hours, and also to account for the inherent randomness involved in fuzzing through statistical tests, we repeated each experiment for 20 times. So in total, we generated a benchmark data set that contains in-depth coverage data that is worth roughly 12 CPU years, which is quite a lot. In the beginning of my presentation, I explained the problem of path collisions. So recall, given two fuzz inputs that execute the program, two different program paths where one path has a higher coverage than another, there's still a possibility that a path collision occurs. So both program paths, even though they have different amount of covered code, have the same hash score. And in that case, the fuzzer maybe says that the coverage increasing input, even though it was executed, has obviously the same hash value and is therefore not added to the queue. And when it's not added to the queue, existing evaluations also do not consider or cannot consider this input, and therefore maybe lead to biased evaluations. So in this paper, the FuzzTastic tool paper, we also present this case study. So the main question of our case study was, how severe is the path collision problem in AFL-based fuzzers? And to evaluate that, or to answer that question, we can use the FuzzTastic dataset that I just mentioned in the previous slide. So in the dataset, we have 7 AFL-based fuzzers, and in total, with the 12 different benchmark programs and the 2 different seats, we have over 3,000 fuzzing campaigns that we can analyze and check how severe the path collision problem really is. For this, we extract a set of basic blocks covered by all generated fuzz inputs for each campaign. Here we can use the FuzzTastic tool, and for each campaign we also extract a set of basic blocks covered by replaying the inputs stored in the fuzzer queue. And then we can use the formula that is provided here on that slide to compute the ratio of missed basic blocks. The results of this evaluation can be seen in this graph here. On the x-axis, we see the benchmark programs for which at least one basic block has been missed. So out of the 12 benchmark programs that we have in our benchmark, 11 programs have at least one basic block that has been missed. On the y-axis, we see the ratios. The white diamonds indicate the harmonic mean values of the box plots, and the red points indicate the fuzzing campaigns with the highest amount of missed basic blocks. And what we can see here from this graph is that there are 2 benchmark programs where only one basic block has been missed, which might be neglectable. And we have 6 benchmark programs where the highest amount of missed basic blocks of a fuzzing campaign lies between 1 and 4%, which is already quite a lot given that the top performing fuzzers are perform very similar. There are only a small difference in code coverage that they achieve. So this already can lead to a biased evaluation. And even worse, here the first 3 benchmark programs, Jasper Free Type 2 and FFmpeg, we can see that there are fuzzing campaigns where up to 9% of basic blocks have been missed when using the inputs that are stored in the fuzzer queue instead of measuring the coverage from all generated inputs. And this definitely leads to a wrong fuzzer evaluation. In summary, in this talk, I introduced the FuzzTastic tool, which is a coverage analyzer. We talked about the artifacts and the steps involved to set up FuzzTastic, how it works, what can be stored, how it has been stored, and how the coverage reports looks like. We also discussed the benchmark dataset that we generated with FuzzTastic, which can be used in further studies. Both the tool and the benchmark dataset will be made available on GitHub on the link that is provided here on the slide. And lastly, we have talked about the case study about the severity of the path collisions and how this can actually lead to wrong and biased fuzz evaluations. If you're interested in the preprint of our paper, please follow the link or just scan the QR code. Thank you.